Okay, I'm going to try to do all of this at once, but this unlikely. Well, in chapter 3.3, they're looking at characteristics of polynomial functions in factored form, and you're going to. This one's interesting. They're showing a line crossing a parabola. By the way, you can find where two formulas meet by making them equal. That's the only time they'll share the same x value, and in this case, they can share 2 points. But then they're also going to discuss family polynomial functions of the same degree. And as an example, these are all parabolas. So they're all x squared, and they all share the same x-intercept. You can have other families. You can have families that share the same vertex, families that share the same slope for lines, etc. And then order. So if you're going to look at the largest x degree, so one with the largest exponent, you're going to figure out the order. So for instance, this is x minus 3 squared times x minus 1. And if you were to expand that, you'd discover the largest degree is x to the power 3. So it's easy to see that this would expand to an x squared. And then if you multiply it times this other x, you're going to get x cubed. So it's also important to remember your rules for exponents. So when I multiply x to the power of a times x to the power of b, it's equal to x to the a plus b. So when I have an x squared and I'm multiplying an x cubed, it's going to be an x to the 5. As opposed to a power of a power, if I have x to the a and I put it all to the power of b, it's going to be equal to the x to the power of a times b. So in the example of x to the square to the third, it's going to be, what's 2 times 3? X to the 6. Important to remember your power rules, and also to figure out very quickly what the largest degree is going to be. So this order is an order of 3. And then they just get you to recognize basic characteristics. And here's a very important skill. They're going to ask you to be able to go both from a formula to a sketch, and from a sketch to a formula. Okay, so let's see here. They'll give you things like this, and they'll ask you to be able to sketch it. Very important skill. Now, if they don't give it into factored form, then you have to factor it. But it's nice that they've given you this in factored form. Notice that it's got a minus, so whatever it is, it's going to be facing down or doing the opposite. And notice it's degree 1 there, degree 1 there, and degree order 2 there, which means it's going to, when we multiply it all out, it's going to be to the power 4. Now most cubics look like an upward facing W, but this minus is going to make it look like a downward facing W. Also notice this. This is going to do something unique. So if I were to sketch this, it's very easy to find the x-intercepts from the factored form. So I'm going to have the x-intercept here at minus 2 comma 0, and that's the x plus 2. I'm going to have it here at 1 comma 0, which is the x minus 1, and I'm going to have it at 3 comma 0, which is the x minus 3. But notice the x minus 3 happens twice. It's squared. Normally the w would start in this quadrant and do that, but because it's got a minus, we're going to start down here. It's going to go through this because there's only one of them. It's going to go up and come down through this because there's only one of them. And then instead of going through 3 to the 0, it's going to bounce back. And it's only going to touch 3 to the 0, 3 comma 0 once. And that's what the square does. If it was cubed, it would sort of do a flat and then keep going. So it kind of bounces back and forth 3 times before continuing on. So be very aware of what a square of the same x-intercept means. It means you're going to turn around and just touch that x-intercept. So if we're going to sketch it like this, you can also add one extra point here, which is the y-intercept, to verify that you got it right. And the y-intercept is always when x is 0. So we get minus 1 in front times 2 times minus 1 times minus 3, which is going to be squared. So minus 3 squared is going to be positive 9 times minus 1 times positive 2 times minus 1 again. So we can see this minus and this minus is going to make it positive, and we indeed have 18, 2 times 9. So we know that there's going to be another spot there called 0, 18. So it's important to be able to figure that out. It also helps you verify that you put the graph in the right spot. So obviously it actually climbs much higher than I've drawn it. They're also going to do the reverse, where they're going to show you the x-intercepts. And let's say I have these x-intercepts and they're going to draw you a graph. Now let's say I have the same thing. And this time it goes right through those spots. And let's say I give you a clear point right there of 0, 3. And then let's say you can also clearly see the x-intercepts at -3, 0, -1, 0, 1, 0, and 3, 0. Well, for this, what you do is you start with your basic formula. And your basic formula, first of all, you got to figure out its degree. Is this to the 3, to the 4? Well, with a W shape with 3 turning points and 4 x-intercepts, my best bet is that this is x to the 4. Because it starts in quadrant 2, it's also got a positive leading coefficient, but that's not important right now. So what I would do is you would write the basic formula, which is y is equal to a times x minus b, x minus c. You can use whatever letters. I think there's very specific letters. And then you just put in as many as x-intercepts as you know should exist. Now, we have a lot of these values already. We just don't have a. And for it to go through x minus 3, we have to have x plus 3. For it to go through x minus 1, we have to have x plus 1. For it to go through x plus 1, we have to have x minus 1. To go through x plus 3, we have to have x minus 3. I should have made them different numbers so you could see which is which. And now you have everything in the formula except what? You don't know a. But we do have a point. It happened to give us a clean point that's not an x-intercept. And you can't use x-intercept to solve the equation. You need a clean new point. And they gave us when x is 0, y is 3. So wherever I see y, I'll put in 3. And wherever I see x, I'll put in 0. What's 0 plus 3? It's 3. What's 0 plus 1? It's 1. What's 0 minus 1? It's minus 1. What's 0 times minus 3? It's minus 3. What's minus 3 times minus 1 times 1 times 3? It is positive 9. So I get 3 is equal to a times positive 9. Therefore, when I isolate 9, I get 3 over 9, which is the same as 1/3, which means I can go back to this a and replace it with 1/3. And now I have the equation of that line. Because I had a clean point, I knew how many degrees, I knew the order, and I also had an inkling of whether the a was positive or negative in case I made a mistake. And that's what this chapter is teaching you. You can see it does it right here. It's giving you the points. It's giving you the clean point of the y-intercept. It's also got this bounce back here, which means that'll be x minus 3 squared. And there it is right there. They just teach you how to do it and teach you how to go through the equation. So here, notice they always give you a clean point. Notice this one has 2 bounce backs, so it's going to be x plus 2 squared and x minus 3 squared. And then you got to figure out your a. And they walk you through it. And they give you some real-time situations, like this represents the path of a dolphin as he leaps out of the water, and the x-axis represents leaping out of the water. And you have to find out, they want to know a couple questions. Write the equation, so you should be able to do the same thing with that. And then they want you to know, I think, when he's out of the water. No, they just want you to write it in a factored form. And sometimes your teacher will want you to expand it. And we should go through a handy tool for expansion. So it's pretty easy to expand x plus 2. And you should know right away it's a squared plus 2ab plus b squared, where a is the first missing value and b is the second missing value. And this quickly you learn a is, in this case, x squared plus 4x plus 4. But what happens when you then have to multiply this thing by x plus, let's say, another polynomial? Now let's just go with x plus 3. Suppose I have to multiply x plus 3 times x plus 4. Well, I'll show you a fantastic trick. You take a box, and along the top you put your one of the polynomials. It doesn't matter which one. And then you divide it up based on each thing. So each one is its own unique thing, plus 4x plus 4. And then since I'm multiplying it by x plus 3, I'm just going to put the x and the plus 3 here. And then you take each box and you multiply it by the thing and put it in this box. So this is going to be what's x squared times x to the 1? X cubed. What's x squared times 3? 3x squared. Now I want you to notice something. What's 4x times x? 4x squared. What's 3 times 4x? Plus 12x. And it's all plus to make it simpler here. What's 4 times x? 4x. And finally, what's 4 times 3? 12. Now notice that this last number is definitely the last numbers times each other, and that this first number is definitely the first terms multiplied each other. But I also want you to notice that these are the same terms. And they also all in this case have plus is in them. So you can only add like terms. So it's very easy to add these together now. I've got x to the 3 here, plus 7x to the square, plus 12x plus 4x, 16x, and the last number plus 12. This box is equal to my new f of x. This box system allows me to multiply these very quickly. Now there's another system where you put them underneath each other, and that works as well, but I really like this box system. Your teacher will teach you as you do it, like multiplication and long division. All right, so let's keep going. Then they summarize it. Very important to have a clean point. And sometimes they don't give you a clean point, and sometimes they don't give you the factors, and you've got to look carefully at the graph. And in this case, notice the clean point we would use is right here, 0, 4. And you want to find one clean point. And it just teaches you what a bounce back looks like and what a triplet looks like. So this one is x plus 3 to the power of 3. So you get this weird little slide going on. So just learn the difference. Then they run you through an example. Match each equation with the graph. Now these are quite simple. Whenever you face a question that you're challenged with, move on to other questions that you know. Do those first. That will build your confidence, and suddenly your brain will also work on these questions you don't know, and you will have aha moments. So let's look at the degree of this first one. What is this going to be if we were to expand it? Well, we can see the first one has an order of 2, and the next one has an order of 1. So if we were to expand it, it's going to be x to the 3, which means it can't be a w. Those are x to the 4s. So you can rule out this one and this one right away. Notice that this has a positive leading coefficient, and both of these are drawn as if not as a positive leading coefficient. This one is doing the opposite of what a normal cubic would do, and almost immediately, without doing any deciphering, I can identify this as the matching graph. However, if I wanted to make sure, I'd look and see if the x-intercepts are there. Yep, there's -1. Yep, there's +3. So right away I can do an extra little bonus of confirmation, and I can even find the y-intercept if I wanted to confirm it even more. But right away I can say that. Then I look at this one and figure out the order. Now obviously this one's order. I've got an order of 2 and an order of 2, which means I'm going to end up, if I expand that, x to the 4. Now because both these w's are upwards facing, this +2 is not going to help me identify it. But the x-intercepts will. So I'll have an x-intercept of -3, -1, and +3. And it's also going to bounce on those because they're both squared. Well, this one doesn't bounce on the x-axis, so I can instantly rule it out. But just to make sure, I can see a +3 there and a -1 there, which means this definitely matches the A. So I can put it right there. The next two should be quite easy because I've already eliminated one of the cubics and one of the quartics, and that's all that's going to be left. So I can see the order of this one is 1, and this is 2, so this is going to expand out to an x to the cube, which means since this is the only one left, that's the only possible matching cubic. However, I can also see -1 is right there, and +3 is right there, in case I'm in doubt, because your teacher won't always make it that easy. So that's that one, and of course it leaves the other one the only possibility. However, I can confirm that oh, did I screw something up? Because this is a cubic, isn't it? No, it isn't. Notice this x here is all alone, and you could miss it, but that's x to the 1, that's to the 1, that's to the 1, that's 1. If I expand it, it's x to the 4. I can also see that this is the only one that goes through origin, which is what that x creates. And then I can see all the points, -1, +3, +5. And I can also see they're all unique. And this is the only one that crosses through the x-axis 4 times. So I have it easily identified. And it's a matter of knowing your basic rules for those things. Then it reverses it, wants you to sketch it for number 2. Now, I might not do all of these because a lot of them repeat the same process over and over again. And if I show it to you once or twice or 3 times, that's fine, but I'm not going to show it to you 100 times. So they want you to sketch this one. Right away, when you're drawing it, there's 2 things you should figure out. The x-intercepts, and is it facing up or down? 3 things you should figure out. What order, what degree or order is it? Facing up, facing normal, or reflected in x? And what are the x-intercepts? And the last one is, what is the y-intercept? Those are the 4 things you should always do to make your life easier. So what is the degree I'm looking at? That's 1, that's 1, that's 1. So I'm going to be looking at a cubic. And then I'm going to figure out what are my x-intercepts going to be. I'm going to be dealing with 4, 0, 1, 0, and -5, 0. So putting them in the right order, it would go like this, from left to right. And that'll just make it easier to draw for me. And then what's the b-intercept when x is 0? I got -1 up front, multiplying -4, multiplying -1, multiplying +5. And I can see that's going to come out as a negative. So it's going to be down below. So -4 times +5 times -1 times -1 is -20, which means it's going to cross the y-axis at 0, -20. If I make a drawing mistake, this will help me a lot. So I'll put it up above. And I'll put it over here. And since I know those x-intercepts, you'll want to put them and mark them clearly. That's how you'll get full marks. If you always label, that's a -5. If you always label, you'll get full marks. 1, 0, 4, 0. And don't forget to label your y-intercept. It's going to be a lot lower than this. So this is not to scale, obviously. Now, since this is a cubic and most cubics go up and then up like that, I know I'm doing the reverse. So it's going to come from up here. It's going to go straight through that. It's got to go through the y-intercept, so it's going to come sharp up again and then quickly through and onwards this way. And you can put those little arrows to indicate it goes on forever. Right there is a fairly good drawing, and you're going to notice it's actually going to look like way down here instead, and then just a quick turn around at the x-axis like that, because this is much lower than this is going to be up above. And you can also plug it into Desmos to make sure. They might ask you for the expanded formula, in which case you should expand the first 2 first. And don't forget, you're going to multiply it all by -1, and then you should expand with the box method times the last one. The box method works for multiplying any polynomial, actually. And then they ask you to do it again for this. Now notice, this one they make it a little bit trickier. And we're going to go through the same steps again. What degree is it? Well, I've got an x to the squared, and I've got an x to the cubed, so it's going to be x to the 5. And most x to the 5 start down here, and they do up to 4 turning points, and up to 5 x-intercepts. Except this one has a cube here, so it's going to do a slide, and this one has a square here, so it's going to do a bounce back. You just have to figure out where x to the 5, since it has a positive, is it facing normal? Yes, it is. It's got a positive leading efficient. What are the x-intercepts? Well, there's only 2 x-intercepts here. It goes through 0, 0, which is what the x squared goes through, and 6, 0. What's the y-intercept? That's the last thing I should figure out. When x is 0, y-intercept is obviously 0. So the y-intercept, when you see 0, 0, right away it's giving you the y-intercept. No need to calculate it. But I also know I normally start here and end here. That's the beginning and odd behavior. I know I've got to bounce back at 0, 0, so I'm going to come up and bounce just at 0, 0. Then I know I'm going to come back up at 6, 0 and kind of do a weird slide thing and then keep on going with an arrow here and an arrow here. And then I'm going to label the only points I have knowledge of, which is 0, 0, and then over here kind of 6, 0, even though there's not enough room. Now sometimes your teacher will want you to find one other point. You might say, how do I do that? Well, you can pick any value for x and throw it in there, and it'll give you a good idea of, the behavior here. For instance, between 0 and 6 is 3. When I get 3 squared, I get 9. And 3 minus 3 there is minus 3. Minus 3 cubed is minus 27. Then I would just simply multiply 9 times minus 27, which instantly tells you this goes way down. Because 9 times minus 27 is like minus 207. So at 3 comma minus 207, it's way down, which will help you get your graphs more accurate. There's other tricks later on. For instance, you're going to learn how to figure out the turning point here. But that's a good example. And then, of course, always just go to your Desmos and put it in there if you want, just to verify your work. This first one's to the square. And sure enough, look at how far down that second turning point goes. It goes way down, and I got the calculations wrong. Oh no, I figured out 3. So if I put that to f of x and just do f of 3, you can see that it's way, I got minus 243 when f of 3. It's way down, and it's not even the lowest point, so you're going to have to learn how to figure out the lowest point. Now, obviously, you could take, your teacher might ask you to use instantaneous velocity to figure out the lowest point by constantly finding the slope. So if it's positive, it's on the right of the low point, and then suddenly if it's negative on the instantaneous rate of change, then you've passed the low point. So some teachers will give you a broad area. They might say it's between 2 and 2.5, and you got to figure it out using instantaneous rate of change. It takes a long time doing that. There's faster methods. All right, keep going. When we're over here, they want you, each member of family quadratic has zeros here and here. Write the equation of the family, determine this. Well, slight waste of time, except for the last one. So you can do all sorts of families. You can put your a value of x plus 1 and x minus 4, and boom, you've done one right there. And then you can do another one. You just got to change the a value. X minus 4, etc., etc., etc. And you can put any a value. You don't even have to put an a value. And those are all the same family because they go through x minus 4. But in the last one, they ask you to find one of these, make one of these go through the point 5, 9. And that's when you put an a in here. And you want to keep these x-intercepts, and you simply replace your y with 9. You leave your a, and you replace your x with 5. 5 plus 1 is 6. And 5 minus 4 is 1. And you discover 9 is equal to 6a. 9, that should be over here. Which means your a is equal to 2/3. And if you plug this in and confirm with Desmos, you will indeed find this. And then if you take the point f of 5, I got it wrong. It's I think I came up with 2/3. No, it's 9/3. Sorry, 9/3. So 9/6 rather is the same as 3/2. So all I did was an accidental little thing. But if I switch that to 3/2, you'll discover f of 5 is indeed 9. And if I go home, I'll see my little graph. It indeed goes through 4, 0, and minus 1, 0. And if I go up to spot 5, way up here, I'll indeed discover it goes through 5 comma 9. Helps if you zoom in a bit. There we go. And that's how you force your graph to go through certain points. Then they write an equation for each of the functions here. Pretty straightforward. We've already sort of done that in the examples. And the secret is to notice the clean point they give you. They'll always give you a clean point here. And they'll give you other things. So for this one, I would say your first thing is figure out the parent graph. What degree is it? Figure out reflection in X or not. And then I would figure out the x-intercepts and do they bounce, which would be squared to the power of 2, or slip slide, which was probably power 3, but power of 5 also looks like slip slide. And then finally, you would ask yourself, and one way to figure out the parent graph is end behavior, start behavior, and end behavior, and also how many turning points and how many x-intercepts. That'll help you instantly. And then finally, once you discover that, write a basic equation using A and use your known point to solve A. So right there, those are always the easiest steps. So I'm going to go right here and figure out my parent graph first. Notice it starts in quadrant 3 and ends in quadrant 1, so it's either a cubic or to the 5 or to the 7. But that's it for sure. Now I notice that there's 2 turning points and 3 x-intercepts, so I'm going to go with x cubed. So that means I'm working with the basic 3 factors. Then I'm going to note that the x-intercepts are minus 3 comma 0, 2 comma 0, and right over here 5 comma 0. And right there, that's enough for me to write this. Y is equal to A, x plus 3, x minus 2, so it's all the opposite of the roots, or the x-intercepts. And now to solve A, what's the point I'm going to use? They gave me 1 comma 8. 1 plus 3 is 4. 1 minus 2 is minus 1. 1 minus 5 is minus 4. This ends up being 8 is equal to 16a. So a is equal to a half. And then I can just go back up, and now I have my equation. And then also don't forget, we're no longer working with y. I know I do y over and over again. Well, we're doing f of x. Boom, I now have an equation. He might want you to expand, he or she might want you to expand it. Just go ahead and start by expanding the first 2 and then using the other one. So practice your expansions. But that is pretty much how you do it every time. Sometimes they won't necessarily give you the clear point, and you've got to zoom out on the graph and find a clear point. For instance, this point over here looks somewhat clear as well. You can't use the x-intercepts. They won't give you clear points. That's about it. Good thing they give us one. They'll also sometimes make the graph just visible that you can find the clear point on your own. Or they might tell you the y-intercept in words. Okay, what about the next one? Well, the next one, I notice it starts in quadrant 3 and ends in quadrant 4, so it's an even exponent degree. I also notice most of them do this, so the a is going to be negative. I can also see 1, 2, 3 turning points, a bounce back here, so that's to degree 2, goes through and goes through. So I'm almost certain this is x to the 4 and that this repeats twice. So if I look carefully at the x-intercepts, I can see that that goes through minus 1. So I can do f of x is equal to a, x plus 1, and I know that's going to be squared because it bounces. And then it's going to be x minus 2 and x minus 4. And then I'm going to solve for a by knowing the clean point they give me is 1 comma minus 12. So if I put in 1 here, I get 2 squared. 2 squared is 4. 1 minus 2 is minus 1. And 1 minus 4 is minus 3. I can instantly see that this is minus 12 is going to be equal to plus 12. Nope, it's going to be equal to, yep, plus 12a. And therefore a is going to be equal to negative 1, which makes sense. And then I go back up here and just put a negative 1 in front, or just a negative. Your teacher might ask you to expand the equation, and it would involve expanding this and expanding that, and then using the box thing to expand them both. Pretty straightforward. And then they ask you to look at these for common families. Common families is pretty easy. It's just essentially see if you can find something in common. So I'm going to try to square the things I see in common. Start with the x-intercepts and put a square around the ones that you think are the same. So I'm looking for minus 3 plus 5. Okay. I got this one. Got that one. Got that one. That one. And careful, sometimes they're tricky and they might have an expanded one here. So I can see that this is x plus 5. And this one is x plus 3 squared. That's what the root of that is. So you have to be careful. Now I'm going to go look at other ones. I'm going to look at the x plus 3 plus 5. So there's an x plus 3 plus 5. There is an x plus 3 plus 5, and this last one's an x plus 3 plus 5. And I can see, obviously, there's also x. Oh, they got this might disqualify it from the family. Oh, no. We're looking for 0 plus 6 plus 8. 0 plus 6 plus 8. 0 plus 6 plus 8. And 0 plus 6 plus 8. So you can see they all go into 3 families. They all share the same x-intercepts. Now that isn't always what makes a family. I believe you can have families with the same vertex or the same slope. But that's a basic idea of what they're looking for. Then they want you to sketch. Now obviously we've sketched a few of them, so I don't know if I'm going to sketch all of them. You can also use Desmos always. But you just want to look at the x-intercepts, so the same process. How many degrees is this going to be? X squared. X cubed rather. Does it have a positive leading function? Yes, it does, so it's going to be like that. Does it have 3 distinct x-intercepts? Yes, it does, so it's not going to bounce anywhere. And those 3 distinct x-intercepts are 0, 0, that's what the x is, so there's not going to be a y-intercept therefore. 1, 0, it's going to be a bit closer. And 4, 0. So those are the 3, and because it has a leading coefficient, I know I'm going to go straight through this, bounce back quite quickly, probably dip quite a ways down and then off. And I'm going to make sure I label all my points quite clearly, and put it in brackets and whatever, and get extra points. And you can even take a guess at this. It's probably going to be between 1 and 4, and the number between that is 2.5. And you could plug that in and get a rough estimate of what the bottom is, but it would be very rough. And you could even do the same with a rough estimate here. And you can see you can get a lot of information that way, and then always throw it back into your Desmos. And actually, I don't know if that's the one I was doing. -4, -1 was the one I was doing. And there was no x in front. Oh, yeah, there was. So right away, I can see, sure enough, notice that it's not quite, the peak isn't quite exactly in between. So it's just kind of gives you a guesstimate. And that the bottom minimum here isn't quite in between. And that's because the slope on this side is much steeper as it heads off into the universe than this slope is. So to see, they're not perfectly matching parabolas. Otherwise, you would indeed be able to figure out the middle point. These max, local mins will come about as you get better. However, at least from sketching, you know that this must be a local max, and that must be a local min. And if they give you one of the values, one of the x values, you can figure, or the y value, you can figure out the other. But it's exactly as we expected it to do. And then you just repeat this process for all of these things. Helps if you just keep your same graph, and please use graph paper. It keeps your scale nicer. Now this one is going to be an x to the 3 as well, except it's facing the opposite, and it's going to go through the following points. And this is B I'm working on. Oy, when graphs don't work for you. Minus 2 comma 0, 1 comma 0, and 3 comma 0. And please note that there has a minus 1 multiplier in front. Therefore, instead of going like this, it's going to start in this quadrant. You can also notice that it doesn't go through 0, 0, so you should figure out your y-intercept, which should be in the negative. So when x is 0, I get minus 1 times minus 1 times plus 2 times minus 3, so it's going to come out minus. 3 times 2 is 6, so it's going to be minus 6, which means there's going to be dot right here, 0, 6. It isn't necessarily the minimum. It's just something it goes through. So if I was going to draw it, I'd draw it something like this. Make sure it goes through 0 to 0 minus 6. And sorry, I didn't quite write that properly. It's going to do this. Going to have a peak slightly to the right. And then it's going to go on forever. And on forever this way. And you want to label each of your points. You know, put a nice dot, put these in brackets. Don't write them right over top the dot like I've done. This is 0 comma minus 6 right there. Make sure the x-axis keeps. And you get a lovely little drawing. This one is squared, so you're going to have a bounce back. And then you want to spot its coefficients. Its degree, it's going to be x cubed again. It's going to go through 0, 0, so you don't need the y-intercept, and 3 comma 0. It's going to go through 0, 0. And keep in mind it goes through 3 comma 0 bounces. Also notice it has a positive leading coefficient. So that means it's going to come up through here, through 0, 0, bounce, and bounce like that. So if I was going to sketch it all nice, I don't think I actually could. And actually the one I just did was pretty good. I'm going to come up, come down, and it's got to bounce and keep going. And that bounce occurs because this is squared. And it goes through 0, 0, so that's the only y-intercept. It can't suddenly come back and go through y-intercept again. That's the other benefit of knowing these things, is you know it has to behave in a certain way. What about this one? Well, this is going to be a slip and slide through minus 1 comma 0. And it's also going to have a, when x is 0, it's going to be 1. So it's going to go through 0 comma 1. So its points here are 0 comma 1. And it also only crosses the x axis once at minus 1 comma 0. And it's going to do a weird slip and slide. Notice it has a positive coefficient. It is a degree 3. So that means it's going to come up, kind of flatten and slide, and then go off into space like that. So that's going to be a little sharper too. It's actually going to slide and go more straight up like that. And you can always confirm this with Desmos. There you go. Very good to have these tools to verify your answers to build confidence. Okay, finally they don't give us a degree 3. When I expand that, I'm going to get x to the 4. And just so you know, this next one is x to the 4 as well. And it's the same process except for one interesting thing. What is the x-intercept for these parts of it? So I'm just going to move them over here. And I'm thinking mostly for these parts of it. Just ignore the x's in the beginning. How the heck do you find this? Well, you set it to equal 0, and you discover that it becomes 2x is equal to minus 1. And therefore, x is equal to minus 1/2. So that means that the point for this one will be at minus 1/2 x, comma 0. What about this one? Well, it's 3x is equal to positive 2, or x is equal to 2/3. So on the other graph, this would be at 2/3 x. Not quite perfect, right? But you have to learn that. And you'll also have to figure out if they have y-intercepts, but you'll see this x here means it goes through 0, 0. So it won't have y-intercepts. So I'm going to do the first one, or sorry, this one here. So e. Faster if I do this. And I'm going to try to do their x-intercepts in order. So it goes minus half, comma 0 on that one, 0, comma 0, 3, comma 0, and 5, comma 0. And notice that it has a positive leading coefficient and that it bounces through none of them. So it's going to go through each of them, which means I'm going to have something like this. And then off into space, and off into space. Now, notice it looks like, yeah, ignore that little part I accidentally did here. Notice that it looks like a W. This is a little bit crooked, but that's okay. And you want to label all your points, and it goes through 0, 0, so it's not going to be a y-intercept, and it goes straight through each of them because they're all unique x-intercepts. This one is going to have 2 bounce backs. So this one still has a 0, 0. And just right close at 2/3, comma 0. So this one's also got a positive leading coefficient. So that means it's going to start up here. It's going to do a bounce, a little W, another bounce, and go up. And just to confirm that, you can do it like this. And I believe it was 2x minus 3 squared. And there you go. There's the bounce. And was it 2/3? 3x minus 2. So you can see how it creates a tiny, tiny bump because they're so close to each other. They're not even one apart. And if you zoomed out too far, you wouldn't see it. So it's just a tiny little bump, but they both bounce back at their spots. Very important to learn that. Makes drawing it a lot faster. Then they ask you, see, these aren't my favorite things to do, is sketch theoreticals. And that's pretty much what 7 through 10 is asking you to do. Sketch an example of a cubic, so you know it's x to the 3, with these zeros. Then write the equation. You can't really write the equation unless you have a clean dot. So, I mean, you can do your best. And just remember that when they give you the zeros, those are the roots. So I'll do a for you, like this. A is going to be f of x is equal to a, because we don't know the a. And it's not x minus 3, it's x plus 3. X and x minus 2. And because they don't give us a clean dot, that's all we could do. Now, they might also want you to expand it, and you should probably do that. And I'm not going to do it. You can also use Symbol Lab to practice your expansion. And then or I should do it in the right thing. So they just give you one x-intercept on this one. We can't figure out the a. And we give it x plus 2 to the power of 3. Yeah, well, it didn't quite do it. So I'll just stick with that to the power of 3. And then number 3, they give us the 4s to the order of 2. So that's going to be this. We don't know the a. It's going to be x plus 1 represents the x minus 1. And x minus 4 to the power of 2 because they told us it was order 2. And then the last one, f of x is equal to x minus a, x minus 3, and then x, not plus a half, but the only way to achieve that is 2x plus 1 And you'll figure out that. Just solve for that and you'll get minus a half. And that one is order 2. They tell us it's power 2. Are they all unique? Yeah, they are, because they all have different x-intercepts. Sketch an example of a quartic function with the given zeros, then write the equations of 2 other functions that belong to the family. 2 other functions, you would just change the a values. And so I'm not going to do it, but I will do the basics. So this time it's going to be a, and I'm assuming there's a. Maybe there's no a. Plus 3, x minus 2, and x. And I'm just going to do them all at once as we go. B, f of x is equal to x. A, we don't know. X plus 2 to the power of 2. And x minus 3 to the power of 2. C is this. You can get quite fast at it. A, x plus 2, x minus 4x minus 3. That's how I can figure that one out. And x minus 5 squared, because it's order 2. And finally, D is very simple. It's equal to a, x minus 6 to the power of 4. So it's going to be a weird flat bounce back. So there you go. Sketch them all if you want. Put them in the Desmos if you want. And just repeat how I figured that out if you want. It's pretty much the same technique as the cubics. It's just using quartics. Okay, for this, you have to factor before you can do it. So this one, clearly, you can factor out 3x from both of them, and you get an x squared left. And when I take x or 3 out of that first one, I'm left with 3/16, so minus 16. And I immediately see that I can factor the next one as x plus 4 and x minus 4, and therefore I have all the x-intercepts. And they've even given me the 3, and I can figure out my y. I don't have to figure out my y-intercept, but I do the same sketches as I did before. I know it's a quartic. I know it has a positive leading coefficient, which means it's going to start here and end up here. It's going to come up through minus 4, 0, which is the farthest left point there. It's going to bounce back and come down through 0, 0, and then going to go up through 4, 0 over here. And you want to label each of your points. And it's actually going to be more symmetrical than this because 4 and 4 on equal sides. And we can see it just by doing it. And hit home. Yeah, the only thing is it goes way up and way down. But you'll probably see that this peak, minus 2.3, 73.9, is reflected down here. Yeah, close anyway. No, it is. And that's because they both pass through 4, 4, and 0. But you can notice that we would have no idea how much we would have to draw that unless we had a couple of other points. This 3 doesn't indicate a stretch, so we'll have an idea that it's stretched more than usual. And then we continue on. So again, it's a matter of some factoring. And I can see that I have an x squared in all of them. So I can take out an x squared, and I'm left with x squared plus 4x plus 4. And I can see immediately that I can factor that last one as x plus 2 squared, which means this is going to be a quartic. It has a positive leading coefficient. So it's going to start in quadrant 2 and go through quadrant 1. And it also goes through the points 0, 0, which is what that x squared is. Oh, and I have one on the left, actually. Ugh, come on. It's going through minus 2, 0, and 0, 0. And it's going to bounce back off of both of them because they're both squared, so it's going to bounce. Bad bounce there. It's going to touch and bounce, and then touch and bounce. This part I drew badly. And there's no y-intercept because it goes through 0, 0. And if you want to sketch it, put it into Desmos. Go ahead. So they're just essentially making you practice your factoring. Now this one's tricky, and you have to go back to your Pascal's triangle to see it. Pascal's triangle reminds you what certain factors are. That's the one I like there. And you might be frustrated by this because they don't teach you how to factor polynomials just yet. And if you don't remember Pascal's triangle, go back and learn it a bit. It's pretty useful. And the secret to notice is, well, there's 3 terms. They each go down by 1. And also to notice, if it's 3 terms, I might be dealing with something that's cubed, because the biggest thing is to the 3. Then you go, oh, this has a natural cube root of minus 3 cubed, becomes minus 27, which means it might fall somewhere into here. And then if you wanted to just take it as a trial, x minus 3, you could possibly expand it to see if it expands to that. So the first expansion will be x squared minus 6x minus 9. And all of it times x minus 3, because my theory is that it's x minus 3 again. Then if I expand that again, I would use my normal box method. And I would treat each of these as a separate entity. And I'm going to put an x and a minus 3 here. And if I do a box like that, and I'm going to draw a straight line through each, like that, and like that, and sorry I didn't quite do it nicely. And then I can just figure out what happens when I multiply each box. I get x cubed, I get minus 3x squared, I get minus 6x squared, so those are going to add up. And then I get minus 18x, so that doesn't add up to anything yet until I come over here and realize I also have a minus 9x. And then finally is it plus 27? Yeah, so that might be an x plus 3 in there, because it's not going to be plus 27, so it could be x plus 3 minus 3 squared, and then a plus 3. So I'm going to try, oh, I know what I did wrong. That first expansion is not minus 9, it's plus 9. That first expansion there is a plus 9. So that means it's going to be plus here. No, it's going to be minus here. No, it's going to be a plus here. And this last one's going to be a minus 27. So that's the only expansion. Now if I add these up, I get minus 9x squared. If I add these up, I get plus 9 and x minus. Oh yeah, this is a plus, sorry. That's another expansion I did wrong. And so then it's plus 18x plus 9x is plus 27x. And this last one's minus 27. So we quickly discover that indeed it is this. Now what's that got to do with Pascal's triangle with the 3 in there? Pascal's triangle says I take the coefficient of 1 and I take the cube root of my first term and my 0 root of my second term. Well, 0 root of 3 is just 1. So it's 1 x cubed, which is true. And then it says I'm going to take plus 3 of my square of my x squared, and then I'm just going to put my other one, which is minus 3 to the power of 1. Because the powers go down for the x squared and up for the 3. So minus 3 times. And there's good YouTube videos for this. So I get minus 9. which is indeed what I have. And then in the last one, I take plus 3, and now my x is just to the power of 1, or x, and my minus 3 is the power of 2 now, which is positive 9. 9 times positive 3 is plus 27x, which is indeed what I have. And then the last one says I just take a plus 1. My x is to the power of 0, which is the same as 1. And my minus 3 is to the power of 3, which is minus 27. And that's the use of Pascal's triangle. You just have to get used to what exponents you put over your first and your second term. Pascal's triangle will allow you to also do to the power of 4 with this line, and to the power of 5 with this line, and to the power of 6 with this line. And Pascal's triangle is easily memorized by putting 1 on the outside and realizing the center numbers will add up. Uh, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And you can derive Pascal's triangle easily on a test that way. So you have to watch out for those tricks that they're doing. I believe they had one more in there of 9. Yeah, they do the same thing with this time with a quartic. I'm just going to bring Pascal's triangle back. And I'm going to look at it with this. And the bummer is they didn't really get you to practice your cubics probably as much as before. Okay. This time we're going to notice, there's a minus in front, so let's get rid of this minus. And maybe this is x minus 5 to the 4, because 5 times 5, oh sorry, to the 3, because 5 times 5 is 25, times 5 is 75. What are we supposed to notice here? It looks like a 5. 5 cubed. 5 times 5 is 25. Times 5 is 25. 5 cubed. But this is x to the 4. Oh, I see. There's an x in there already. So you've got to factor out minus x. It's sometimes really tricky. So you get minus x, and you're left with x cubed minus 15. Oh, plus 15 because I took out a minus x. X squared. And then I've left with a plus 75x. And then the last one, plus 125. Now I can see that I'm dealing with a cubic. And my cubic is most likely x, since they're all plus, 5 to the cube. Now you can verify that with Pascal's triangle by taking the 1, 3, 3, 1. And then if I do x cubed plus x squared times the 5 to the 1. Sure enough, that's 5x squared, isn't it? Did I get it? No. Hang on. Cube, so it's going to be 5. Interesting. It should be 5, not 15. 5 to the 1. I'm going to do Symbocourt, and Symbolab rather, and I'm going to let it expand for me. Minus x and x plus 5 cubed. Actually, let's just let it expand x plus 5 cubed first. Oh yeah, it does do 15 x squared. Oh yeah, stupid me. My God, I forgot to put the 3 in front, and then it's 5 to the 1, and 3 times 5 to the 1 is 15. And then I got to put the 3 in the front, and that was x squared, by the way. then it's going to become 3x, and then it's going to be 5 squared, which is 25. 5 times 20, 3 times 25 is 75. And then finally, the last one is simply going to be 5 cubed, which is 125. So you can see that is indeed how you'd use Pascal's triangle if you remember to put the 3 and the 3 in front. So we can indeed see that this is the expansion of it, and that allows you to graph it. Now, obviously, if they're asking you this and they haven't taught you yet how to factor polynomials, you have to look for tricks like this. And then they're giving me just several 3 zeros, 3 turning points, and I'm not going to sketch this. I'm going to describe what you should come up with instead. Okay, so for 10, if it's degree 4, we're talking x to the 4. It has a positive leading coefficient, so you don't have to worry about it. It's going to have 3 zeros, which means it goes through the x-axis only 3 times. For it to do that with a degree 4, one of those has to be squared, and it has 3 turning points. So it has the normal turning points. So what I would say, if you're going to design it, it's going to be, might as well make one of them x. Might as well make one of them x squared, actually. And then the other 2 can be anything. So that's going to have 3 zeros, it's going to have 3 turning points, and it's going to have a positive leading coefficient, and it's going to look like this. It's going to come down, it's going to go through, x is 0, it's going to come up, touch the 0, bounce back, and then go up through the x is, so minus 3 is here, and plus 2 is there, and the 0 creates the bounce back here. So now it has 3 turning points and 3 zeros as required. Then this one has a negative leading coefficient, also degree 4, and it only has 2 zeros and 1 turning point. 2 zeros and 1 turning point. That's interesting, actually. 2 zeros and 1 turning point. So that could be an x squared and anything else. Let's say x minus 2 squared. And then you can just put a negative 1 here. So it's going to bounce back here. But that's 2 turning points. How do I create 1? Oh, I know what you do. You make just x minus 2 normal, and you make it x cubed. So when I draw it, it's going to be reversed. It's going to slip and slide through this. And then it's just going to come down through minus 2. So I'll show that to you on the graph. So if I just make 1 cubic, and let's say 1x minus 4, and then I'm going to put a negative in front of it just because that's what they wanted. You can see that this slip and slide does not count as a turning point. It only turns down once, and we can see we have 2 zeros. And the only way you can create 1 turning point with 2 zeros is if one of them is cubed. Because if they're both squared, you're going to get 2 turning points. Or 3, yeah. See? So that doesn't work. And then they say a degree 3, negative leading coefficient 1, 0, no turning points. That's easy. That's negative x cubed if it's no turning points. There, just like that. 1, 0, no turning points. So they just want you to understand the nature of these. Now, here, 11 looks hard, but it's not. The secret is find the zeros, find the y-intercept. Read the questions well, always, twice. So they're asking you to sketch a graph of the data of a 15-year period, and it's of profit in thousands of dollars. And they're counting 1990 as the x-axis, so the years, and 1990 represents year 0. That's important. They ask you to write the polynomial equation. Well, first of all, I want you to notice the zeros. It goes through 0, y, so there's the y-intercept. No, that's an x-intercept when y is 0. And here's another x-intercept when y is 0, and here's another x-intercept when y is 0. And I also want you to remember that they're calling 1990 that the x is 0, so you're going to discover the y-intercept in red here. Which means if I'm graphing this, I can see I've got 3 zeros. And I can also see in the beginning it's negative and it's going up, right? And if I have 3 zeros, I'm probably talking about a cubic. So that means if I'm going to do here, like this, and I know that it starts way down here in the y value of 0, comma, negative 216. That's my y-intercept because it's given right away. 1992 represents 2 years later, so it has a x-intercept of 2, comma, 0. This represents 9 years later, so it has an x-intercept of 9, comma, 0. And this represents 12 years later, so it has a 12, comma, 0, which means it's going to come up, go through 2, 9, comma, 0, go way up high, come down through 9, comma, 0, and then go back up. So we're talking about an x cubic with 2 turning points and 3 x-intercepts, and we have a clean point. So that means I can rewrite this as y is equal to a, and I don't know a, x minus 2, x minus 9, and x minus 12. Those are the intercepts. And I also know one clean point. When y is minus 16, minus 216, x is 0. So it's going to be a times minus 2 times minus 9 times minus 12. And I'm going to discover it's minus 216 is equal to minus 216a. So a is positive 1. A is equal to 1, which means my equation has no a. And this will be it. X minus 2, x minus 9, x minus 12. My hands are starting to fail, usually a sign of fatigue. Anyway, if I do my f of 0, I'll discover a value way down here, minus 216, just as expected. And sure enough, I'm going to get the data points I want. Let's take f of 4 to see if we get 80. Sure enough, we do. Let's take f of 10, that's the year 2000, to see if we get minus 16. Yeah, we do. And we can even ask it to make a table here of this graph and just put in all the years we want. And I want you to have a good look at it. And I'm going to copy it. And see if we get the same table. I don't know why it won't let me. I think because I don't have enough room, so I'll just try to do it like this. Yeah, there we go. And sure enough, I'm going to get the same values. 216, minus 88, 0, 54, 80, 84, 72, 50, the exact same values. And if I was going to describe what happens here up to year 14, in year 14 it's dipped down and it starts to climb again, yeah, right there, I will say it's a gold rush. People left the town, there was some sort of plague, and then they came back. And what restrictions should be placed? Well, we only know 0 to 14 on the domain, so that means 0 is smaller or equal to x is smaller or equal to 14. Do they ask anything specific? Sketch, if x represents the number of years, oh, it's profit and loss over a 15-year period. So for some reason they lose money wherever it dips below the x value, so they started at a loss. In year 2, they started making money. For some reason, between year 9 and 12, they started losing money. And then the sky's the limit. They just took off from there. Sometimes this occurs in companies when demand disappears or there's no material to make their items. Um, so you can come up with explanations. Determine the equation of the polynomial from each graph. It's the same thing we've been doing. So very quickly, I'm going to do it. And you're going to start by noticing a cubic, and it's normal, so it's got a positive a. They've given us a clean point, and I can see right away this is going to be my a. It's going to be f of x is equal to a, and it's going to be x plus 2 and x minus 1. And there's also an x plus 1 in there right away, and then I can figure out from my clean point, I can figure out my a. So I can see minus 2 is going to be equal to minus 2 a, so a is going to be equal to positive 1. So that's going to be it for that graph. The other one, I can see that my a is going to be reversed, and I can see for b, my f of x is equal to a x plus 4, and all I'm doing is doing the x-intercepts in order, and there's no bounces backs or anything, so they're each unique. And then I'm going to figure out my a from my point given, which, oh, it's tricky, I almost put in 16, it's 1.6 a, and now minus 3 makes it tricky as well. So I can see minus 1.6 is equal to 4a, which means a is equal to minus, which makes sense because it's upside down, 0.4. So that means this a up here is minus 0.4. And if I do this, I'll get that graph. Determine the quadratic function that has zeros at minus 3, 5 if f of 7 is equal to minus 20. Okay. That's the same. I mean, we've done this. It's actually one of the easier questions. And I'll have to quit soon. So we're dealing with quadratic. So all I know is f of x is equal to a. And it has x plus 3 and x plus 5 in it, because that's where the roots of x minus 5 and minus 3 exist. And I also know that when x is 7, y is minus 720. I'm just adding 7 and 3 and 7 and 5. So I know that minus 720 is going to be equal to 120a. Therefore, a is equal to minus 6. So I go back up and do this. And if I was to punch in a Desmos, I will indeed get the rules I want. Then they just do the same thing, but this time with a cubic. And these are the zeros, represented in factored form, so the opposite signs. And then I know that when y is 28, x is 5. 5 plus 2 is 7. 5 minus 3 is 2. 5 minus 4 is 1. I get 28 is equal to 14a. So therefore a is equal to 2. So I can go back and put in that. Not hard. We've actually done a gazillion of these already. All right. Now it's important that you do them yourself, because the whole point of me doing them is that you stop the tape and you do them. It's not for you to copy this into your homework. If you just copy this into your homework, you're actually doing yourself a huge amount of problems when the next course, because every math course is built on the knowledge of the previous one. So if you don't know what you're doing, you'll never succeed. Now here they just kind of get rid of our A, B, C, D, and they tell us that down here this multiplier of k will repeat twice. Now they also tell us so I guess I just had to do that. Okay. So all they're doing is adding an extra missing bit of information. They tell us it has a 0 when this occurs. We know it's a cubic. Determine the value of k. Then rewrite. So that tells us that one of the factors is x minus 2. That's all it tells us. All right, let's see if it's possible to do it. So that means that when y is 0, x is going to be when x is 2. So if I take the equation and work with what I know, well, and there's a plus 1, and I'm just going to start with the information they gave me to see if it gets me anywhere. So when y is 0, x is 2. What's 2 cubed? 8. What's 2 squared? 4. What's 4 times 8? 32. Minus 32 times minus 8. Then I get minus 2 because it's plus 2. And then I get 3k, which tells me nothing, and plus 1. And remember, that's k times 8. So that means 0 is equal to 8k. It's an easier way to write it. Minus 32 minus 2 plus 1 is minus 33 plus 3k. So that means 1133 is equal to 11k, which means k is equal to 3. So now I can rewrite it. It's 3x cubed minus 8x squared minus x, and then what's 3 times 3? 9 plus 1 plus 10. And there I have the full equation. And by the way, this is supposed to be, yeah, minus 1x. There we go. And that's the full equation. It's very easy when you work with what they've given you. There's very little you can do. But then they say determine all the zeros. Okay, that's interesting. Determine all the zeros. So we know one of the factors is x minus 2. So they essentially want to know what happens when I take 3x squared. Let's see if I can use their values here. So I know it's going to be 3x squared minus 8x squared minus 1x plus 10. And I know one of the factors when x is 0 is x minus 2. So the question is, if I factor x minus 2, what do I get? Well, I don't know if they've taught you enough. Oh, they want you to graph it first. Okay, well, you could go ahead and graph it and then figure out all the zeros. Okay. There is a way of doing it, but they haven't taught you yet. So if I graph it first, get rid of this. 3x cubed minus 8x squared, was it? Minus? Was it minus? Minus x plus 10. The zeros will reveal themselves, and then you can just rewrite it. So it's going to go through x2 and x minus 1. And let's have a look at this again. Yeah, and it's going to be it's going to go through that. Oh, it's got to bounce back twice here. Here we go. So it's got another one, x minus 1.67, which is interesting. That's probably 3x minus 2. No, hang on. So this one, 1.67, is the same as 5 divided by 2. Is it 5? It's 5/3. Yeah, it's 1 2/3. And 5/3 is the same as 3x minus 5. Oh, almost. I got it going through the same thing. Except this 3 is not accurate. Oh, it's got no 3 in front. Okay. And there we go. And you ask yourself how I came up with this one. It's because I knew that was 1.667 is the same as 1 2/3, and 1 2/3 is the same as 5/3. And if you solve this for 0, you'll see that x is equal to 5/3 when you solve that. And because I graphed it, they allowed me to see. And they essentially allowed me to use the visual representation of the graph. You might say, how would you do this on a paper? Oof, it's a good question. If they didn't let you use graphing calculators, I think it would take a long time. Describe what you know about the graphs of each family as much detail as possible. So there's an x-intercepts that bounce back on 2 and 4. And there's x-intercepts that goes through -4 but bounces on +3. This is a quartic. This is a cubic. Depending on A, it depends what A is, positive or negative. And this one will look like this, bouncing on those x-axis. And if it's negative A, it's going to be bouncing like that. And the same with this one. It's going to go through -4 and +3. So it's going to go through -4 +3 and off, or it's going to go through -4 +3 and off. Let's see, -4 +3. Oh, it's going to bounce, sorry. So here it's going to go through -4 and bounce on +3. And if it's negative, it's going to go through -4 and bounce on +3. All depends if the A is positive or negative. And this has 2 bounces on the x-axis, and this only has 1. Yeah, that should be good enough. 16, cut the corner. Oh, boy. Jesus, I don't know if I could do this. So feel free to stop if I can't, because I might have to stop myself. So we got from a 30 piece of cardboard, we're cutting the corners off. So I got a rectangular piece of cardboard, and I'm cutting. 4 remaining tabs are folded upwards. Square corners are cut. So we got square corners. So that's good to know. Square, square, and I assume they're all the same. So that's going to create a tab where you can fold up this part and this part to create a box. The volume of the box is given by this, and you can actually rearrange that to figure out the x-intercepts, where x represents the height. So the height here is definitely going to be this part here, which means the box corners that they cut out here are x and x. Calculate the volume of the box with a height of 2. So that means if x is 2. Yeah, so the x here is going to be 2. That's all there is to that. Calculate the dimension of the box when the volume is this. So then you set the volume to this, and you've got to figure out what your x is. That's a tough one, actually. I'm going to just let Desmos for the interest of argument's sake, but I'm also going to show you that if we look at these, -2x plus 30 is equal to 0 is going to be x is equal to 15. So it's going to go through 0, 0. It's going to go through 15. It's going to go through -2x plus 10. It's going to go through 10, 0, and it's going to go through 15, 0. It's also got positive leading coefficient. It's a cubic. So it's going to go up, down like that, and up. Now the volume's only going to be positive from here and from here. And so the first question, when we're dealing with 2, the volume's going to be somewhere around there. The second question, when we're dealing with a volume of 1,000, the x is going to be much bigger. The first solution, A, is easy to calculate. It's 2 times, what's 30 minus 4? 26. What's 20 minus 4? 16. So the volume is going to be equal to 26 times 16 times 2. Volume is going to be 832. So it's actually possible that there's 1,000 volume here. And actually I will say it's both here and over here. There's going to be 2 volumes like that. There's 2 possible volumes of 1,000. Calculate the dimension of the box when it's 1,000. So for that, solve when v is bigger than 0. So that's between 0, 0 and 10. So between x values of 0 and 10. And when x is bigger than 15. All other volumes are negative. See? And then calculation when it's 1,000. So then we'd have to say 1,000. This is a little tougher. 1,000 is equal to x times, and I like to do it in order here. They've kind of cheated. You should actually expand this to solve it. And actually, that's a good point. You would expand it first, and you would get this minus 2x squared plus 30x, and then you would multiply that by minus 2x plus 20, because that's the only way you're going to get the 1,000 to the other side. So this next one is minus 4x cubed, and you could always use symbol add for this, minus 40x squared minus 60x squared, so minus 100x squared. And then the last number is going to be, well, you're not even going to have a number. So I'm going to get Symbolab to expand it for me, but that's your first step. You're going to expand it. So I'm going to expand x minus 2x plus 30 and minus 2x plus 20. So your first step is to expand it. And it's going to expand it to this for you. Which I believe is close to what I had. Yeah, it is. I just didn't do the last expansion. And all of that is equal to 1,000. And if you get the 1,000 on to the other side, all of that is equal to 0. So now all that is done is it's lowered the entire graph you had by 1,000 and created a new x-axis. So now if you can solve this, you can figure out all the values that are true for x that essentially equal 1,000. Interesting stuff. I think to solve it, I'd have to put in some values of x first. And probably, since we know 2 is 800 and something, 3 is probably a valuable one. So I'm just going to let Desmos solve it for me, but that's how you go around about doing it. So y is equal to 4x cubed minus 100x plus 320x, and then I think it's x squared. Was that the expansion? Minus 80x squared plus 300x. So I got my middle term wrong. Plus 320x plus 100 plus 300x. So you can see that this is the same graph that we were figuring out. And you can see that it is indeed what we were graphing. And then if I subtract it by 1,000, I have the question they're looking for. So now my x-intercepts, and we can see that all the other graph has disappeared, and we can see that this is the only x-intercept that works, 16.348. So now if I go back to this and change this to f of x, we can see that f of 16.348, 9 or whatever it was, yeah, 8, a little less than 8, 7, 9, 7, 8, 7, 7, 7, 6, 9, 8, 7, 6, 5, 9, 8, 7, 6, 4. And so that's pretty close. So that is the value of x that will give me a volume of 1,000. And there's only one of them. So if I was to label like 16.347 comma 1,000, we'll see that the only place, because the max volume of that first dip is only 315, so I got that other volume wrong. And we can see that the only time we're going to hit a volume of 1,000 is way up here. And then also if I do f of 2, it'll tell me the volume was 312. So I got the calculation wrong with 312. So I think 2 minus 4 plus 30, 26, minus 4, 16. Yeah, I think I got that way wrong. Calculate the volume of the box when the height is 2 should have just been replacing the 2 in there. See if I got the actual thing right with the original roots. X, 30 minus 2x. And the other one was 20 minus 2x. And I'll call it G so it doesn't conflict with the other one. And I'll do G of 2. 832. Yeah, that's what I got. So it means I got the expansion wrong. Yeah, let's try the expansion. Plus 600. Yeah, I got the expansion wrong. And it was 100. So I did have the original thing wrong. And we can see now that there's going to be 2 possible volumes, as I correctly guessed the first time. So I actually screwed up the second time. And how you can do this is you make your 0 equal to your equation, and it will draw, 1,000 equal to your equation. And it should draw out the 2 lines that work for you. So if you zoom in, no, maybe not. Well, you can also do it like this. You can draw a line at y is equal to 1,000, and it'll tell you the several points that x can be that will make the volume 1,000. X can be 2.8, x can be 5, and x can be 17.071. To solve this, you would do the expansion here and simply subtract 1,000, and then you would have to factor out this new line to figure out where it crosses the x-axis. Oh, and you know what? Because we know, no, this one's not perfect. So we'd have to figure out the 5 to have a really good chance. Very hard question to do without knowledge of how to factor these. I hope you sort of understood what I was going for, though. I just couldn't. I know how to factor it with my current knowledge, but I don't know how to factor it with the knowledge they've taught you so far in this chapter.